Now we are going to discuss the solution of partial differential equation by the method of separation of variables, and this method is also called product method. This method is applicable for solving linear partial differential equation involving derivatives with respect to two independent variables. See, to apply this separation of variables method, the two conditions are given. So these two conditions we have to remember. The one is the equation must be a linear. Linear means the degree of the dependent variable and its derivatives must appear as 1. The degree of the dependent variable and its derivatives must be 1. That is what we call linear PDE. And also other condition, one more condition is the equation must contain two independent variables. So remembering these two conditions, we have to apply the product method. Okay. Now adding to this explanation, I'm just give the some differences between the previous method which we discussed. That is, see here, suppose the equation is non-homogeneous. So here I gave one example, dou square u by dou x square equal to x plus y. So this is the non-homogeneous partial differential equation containing either only one independent variable or two independent variable. This point you remember. The equation must be a non-homogeneous, but it contain either one independent variable or two independent variables. In that case, we apply the direct integration method. This is the one method already we discussed in the previous video. The other method is converting the partial differential equation to ordinary differential equation. Okay, this is the one method where the partial differential equation must be a homogeneous and containing only one independent variable. So these conditions you have to remember. The equation must be a homogeneous, it must contain only one independent variable. Then we convert the partial differential equation to ordinary differential equation. Then we find the solution of the given PDE. For the direct integration is what? I repeat again. The equation must be a non-homogeneous. It must contain one independent variable or two independent variables. Okay. Then we apply the direct integration method. Now in this discussion, that is the method of separation of variables, the equation, the given PDE must be either non-homogeneous or homogeneous. Even it is a homogeneous, we apply this method. Even if it is a non-homogeneous, we apply this separation of variable method. Okay, for both non-homogeneous and homogeneous. And the other condition is it must contain two independent variables. See, this is the non-homogeneous containing two independent variable. So this is and also homogeneous containing two independent variables. So for this condition, we apply the product method. Okay, now what we do in this, first, so here is the procedure. If x and y are independent variables, z is the dependent variable, then we assume the solution in the form z equal to x into y. So the capital letters here we used, where capital X is a function of small x, capital Y is a function of small y. Okay, so what we do in this step, suppose the partial differential equation is given in terms of z, which is a dependent variable, then independent variables are x and y, and the partial derivatives of these. Then we assume the solution in the beginning we assume the solution as z equal to x into y. Okay, so depending on the independent variable, suppose the independent variables are x and small t, then we assume the solution as z equal to capital X into capital T. Okay, when we have x and t, then we assume capital X and capital T as a solution. Clear? So this is the first step. The second step is we substitute this wherever the z is there, we are putting z equal to this x into y. Okay, where partial derivatives present in the equation converts to ordinary derivatives. Means whenever we are putting z equal to x and y, so where that z is there, we are putting z as a x into y. Okay, so then we convert the partial derivatives to ordinary derivatives. Then the resulting equation involving ordinary derivatives. Okay, because when we convert the or partial derivatives to ordinary derivatives, then what we do, we rearrange the derivatives, we rearrange the terms in such a way that LHS is a function of x, RHS is a function of y. Means in this step we are going to separate the variables. We are going to separate the variables, that is x and dx on one side, y and dy on other side. So that's why this method is called method of separation of variables. So after the separation, when we take x and dx on one side, y and dy on other side, then we equate each side of the equation to a common constant. We equate both. This LHS equal to same one constant and RHS equal to the same constant. Okay, we are equating the one common constant, then solve the resulting ODE. So after equating LHS equal to constant, then RHS equal to the same constant, that ordinary differential equation we solve for capital X and capital Y. So here the overall that method is, and even this method is called product rule, because we are considering the solution as a product of independent variables, that is x and y. So here our work is to find the values of capital X and capital Y. Okay, which is in terms of small x and small y. Okay, then the last step is, after finding the values of capital X and capital Y, we are going to substitute the values of capital X and capital Y in the assumed solution. In what we assumed is z equal to x into y. So in this we substitute the values of x and y. Okay, then we get the required general solution of z. Okay, so here is one example. You first analyze the nature, what as in the explanation, what are the conditions. The equation must be either homogeneous or non-homogeneous. Okay, and it must be linear. See, here u is the dependent variable, x and y are the two independent variables. The first condition is what? It must be linear. S, the degree of the dependent variable and its derivatives are 1, and the other condition is it must contain two independent variables. Yes, so this is the given PDE. So where capital x and y are the independent variable, so we assume the solution as, so as a u is the dependent variable, we take u equal to capital X into capital Y as a solution. We assume this as a solution where capital is a function of small x, capital Y is a function of small y. Then we substitute the value of u in the given PDE. We substitute here. Okay, see, dou u equal to xy divided by dou x plus dou of u as a xy divided by dou y equal to 2 into x plus y, and here u equal to xy. Yes, we substituted value of u. Then what we do, we have partial derivative with respect to x. When we have partial derivative with respect to x, so definitely y is constant. So I keep this y constant outside, then it is dou x by dou small x. Then we have partial derivative with respect to y, so x is constant, keeping x constant outside, dou y by dou small y equal to 2 into x plus y into capital letters x and y. Okay, so as by the procedure, we convert this partial differential equation to ordinary differential equation. Then by this y as it is, so this partial derivative I converted as ordinary derivative dx by d small x plus capital X as it is. Then this partial derivative converted to ordinary derivative dy by d small y equal to 2 into x plus y into xy. Then what is the next step? What is the next work? We separate the variables. The variables are, we separate small x and capital X on one side and small y and capital Y other side. That is what the next work. We separate the variables. How we separate? First we divide by xy. So when we divide by xy, y cancelled, we get 1 by x into dx by d small x plus, here when we divide by xy, x cancel, 1 by y into dy by d small y equal to this xy cancel, so 2 into x plus y. Now we separate the variables. See, 1 by x dx by d small x, I take this 2x this side minus 2x equal to, then taking 1 by y dy by, divided by d small y this side, then this plus 2y. Okay, see, functions of x on one side, functions of y on other side, then both we are equating to a common constant. Then taking this LHS equal to the constant, then RHS equal to constant. So again in this step we are going to separate functions of capital X on one side and the functions of small x on other side. So two times we are separating the variables. In the first step we separate small x and capital X on one side, small y and capital Y on other side. This is the one step. Again in this we separate capital X on one side and small x on other side. See, 1 by x dx I keep, taking this dx this side, again we separated the variables. Similarly in this, minus 1 by y dy, so this we can rearranging this, 1 by y into dy by y equal to 2y minus k. So again separating 1 by y dy, taking this dy to that side. Okay, so here also we separated the variables, capital letters one side, small letters. Okay, now the next step is integration. After separating the variables, we know the procedure, that is on integration. So integration of 1 by x. Okay, so integration of 1 by x is log x. Okay, then integration of 2x. So integration of 2x is 2 into x square by 2, 2 to cancel. So here we get x square plus integration of the constant k is k into x plus integration constant. Similarly log y that is integration of 1 by y is log y equal to 2y is y square minus k integration is k minus k into y plus integration constant. So therefore the value of capital X is e to the power, okay, e to the power x square plus kx plus c1, then capital Y value is e to the power y square minus ky plus c2. So now we got the values of capital X and capital Y. So these values we substitute in the assumed solution x and y. Okay, this is the x value and and adding, so multiplying these two and keeping the constants, that is e to the power c1 into e to the power c2, that is e to the power c1 plus c2, and taking variables on one side. Okay, then this is e to u equal to e to the power x square plus y square plus k into x minus y, and this we take as a constant c. Okay, so this is the solution. Similarly I explain one more example. by the method of separation of variables. See, this is homogeneous PDE containing two independent variables. So that point you please remember. So here dependent variable is z, independent variables are x and y. So we assume the solution as a dependent variable z equal to independent variables are x and y. So capital X and capital Y. Okay. Now we substitute this value of z in the given PDE. Dou square z equal to xy divided by dou x square minus 2 into dou of xy by dou x plus dou z value xy divided by dou y equal to 0. Okay. Now so we have the partial derivative with respect to x. Okay, so y is constant, keeping y constant, dou square x by dou small x square minus 2. Again here y is constant, then dou x by dou small x plus here x is constant, keeping outside, dou y by dou small y equal to 0. So now after this we convert the PDE to ODE. So we write this partial derivative to ordinary derivatives like y into d square x by d small x square minus 2y into dx by dx plus x into dy by y d small y equal to 0. So again next step is after converting to ODE we separate the variables, that is dividing by x into y. This so dividing by xy is common in all the problems. So we get 1 by x because y cancelled, 1 by x into d square x by dx small x square minus y cancelled 2 by x into dx by d small x equal to, so taken this term that side, that is x cancelled minus 1 by y into d capital Y by d small y. Yes, we separated the functions of x and dx on one side, y on dy other side. So we equate the common constant k. So we're taking the LHS equal to this constant, then RHS equal to constant. So now we are going to solve these two ordinary differential equations. Yes. So here the first ordinary differential equation, which is the second order. We have a second order equation, right? So when we have the second order equation, we know the procedure. We write the auxiliary equation, that is m square minus 2m minus k equal to 0. So we cannot factorize this as we have some general constant. So we apply the formula m equal to, that is minus b. Minus 2 means this has become plus 2 plus or minus square root of b square. Minus 2 square is 4. Okay, then minus 4ac minus 4 c is minus k, so it become plus 4k divided by 2a. A is 1 divided by 2. So taking 4 common outside the square root, it is 2, 2, 2 and this 2 cancel. Therefore the roots are 1 plus or minus square root of 1 plus k. So here these are real and different roots. These are real and different roots. For real and different roots we write the solution. So here capital X is the dependent variable, right? Therefore x equal to c1 e to the power first root 1 plus square root of 1 plus k into x, because x is the independent variable, plus c2 into taking the second root 1 minus square root of 1 plus k into x. This is the solution for this second order equation. Similarly for other ordinary differential equation, d capital Y by d small y plus ky equal to 0. So for this also we can write the auxiliary equation as m plus k equal to 0. Therefore m equal to minus k. So this is the one real root. For one real root we write the solution as capital Y equal to, we take the another arbitrary constant c3 e to the power minus k into y. You know how to write the solution when we have a one real root. Okay, now this is the one, so this is the value of capital X and this is the value of capital Y. Therefore we substitute these capital X and capital Y in the assumed solution z equal to xy. So this is the value of x, this is the value of capital Y. What we just simplify this and we put in the standard form. How? E to the power x, from these two e to the power x common, then here we have e to the power minus ky. From these two I took e to the power x here, then e to the power minus ky. What remained? I multiplied this c3 into c1 then what remained? E to the power square root of 1 plus k into x. Then again multiplying this constant c3 into c2 e to the power minus square root of 1 plus k into x. Okay, so this we can write e to the power x minus ky. I take this as a common constant as a into e to the power square root of 1 plus k into x, plus this again taking the another constant as a b, then e to the power minus square root of 1 plus k into x. So this is the required solution of the PDE, and this is what we call the solution of the partial differential equation by separating the variables or product method. Thank you.